Okay, in this brief history of the atom, I'd like you to take a piece of paper, or imagine you're holding a piece of paper and tear it in half. And then take one of those pieces and tear that in half. And then one of those pieces and tear that in half. And keep tearing the piece of paper in half until you get so small that you can't grip it to rip it anymore. And then imagine, right, in your mind, as Democritus did before there was scientific experimentation, a thought experiment. Just imagine that you could keep ripping that paper in half until you got to the tiniest bit of matter that made that paper paper. Okay, he used the term atomos in Greek, meaning indivisible. So he imagined in his mind that you could get to a point where you would reach the smallest bit of matter that made that paper. And he said that smallest bit of matter was indivisible, so you couldn't tear it any smaller. And he used the term atomos. Now, unfortunately, Democritus' idea did not receive a lot of support by reputable philosophers at the time, and so his idea was not pursued really for almost another 2,000 years, until we have James Dalton, who was doing scientific experimentation and proposed the idea of atoms. So Democritus's thought, right, comes back, and James Dalton proposes that we have atoms that make up matter. He said atoms of different elements will be different sizes, which is actually true. He said that atoms of a certain element, so atoms of the same element, are going to be identical in their physical and chemical properties. Well, we know that atoms of the same element can actually have different masses. And so the concept of isotopes, atoms of the same element that have different masses, is actually, that's a true statement. And so atoms of the same element are not perfectly identical. Atoms cannot be divided, created, or destroyed. Well, we know about nuclear fusion and nuclear fission now, so in fact we can subdivide an atom or fuse two atoms together to change their nucleus. Certainly atoms do combine, atoms of different elements do combine in different ratios to form chemical compounds, and they can be rearranged, right, in chemical reactions. So Dalton was proposing this idea of a simple sphere. So think of this in 3 dimensions, right? And he called, I guess I should say singular here, he called this an atom. Okay, after him, and again, we're touching on a few of the main people here. So moving on to J.J. Thompson. Okay, J.J. Thompson's model is often referred to as the raisin bun model or plum pudding. I really think, maybe a chocolate chip muffin model might be more appropriate for these days if you're familiar with a chocolate chip muffin. How does Dalton's model change? Well, we're still thinking of the atom. I can get that drawn in a circle. We're still thinking of the atom as spherical in shape. Okay, but now we think of this as being a very positive, right? A positive sphere. So the entire sphere here is positively charged. And then throughout the atom are negative charges. Okay, Thompson did an experiment called the cathode, or with cathode ray tubes. And he found that particles in a beam actually moved towards a positive plate. And so because it was known at the time that opposite charges attracted, and so if the plate that is positive that the beam is attracting to, he inferred that the charge of the particles in the beam must be negative. And so here he was really discovering the electron. So if you think of this as a chocolate chip muffin, really the positive part of the atom is really like the batter or cooked batter of the muffin, and the negative particles are like the chocolate chips, all spread throughout that sphere, throughout the muffin. Okay, so we move on from, well, if you wanted a name, actually, I never said this, if you wanted a name for Daltons, right, you might think of it as a billiard ball. A billiards is pool, if you're familiar with that, maybe you want to have a look. But basically, just think of it as a sphere, just a simple ball. Okay, J.J. Thompson, through his cathode ray tubes, proposed this model of the atom, which you can think of as your chocolate chip muffin, right? Chocolate chip muffin model. So again, the batter is positively charged and throughout the atom, and then we have the negative electrons embedded. And then we moved on, and Rutherford came along with Ernest Rutherford with his gold foil experiment. So Rutherford was trying to confirm Thomson's model of the atom, and he sent a beam of positive particles, which were helium nuclei, the nucleus of helium atoms. So he sent these positive particles towards a very thin strip of gold foil. So this is think of aluminum foil in your kitchen. Now think of a strip of gold foil. Instead of aluminum, it's made of gold. And then he had a detector. So there was a detector around here. And so he was looking to observe what happened when the beam of positive particles struck the gold foil. Okay, he actually said that it was like shooting a bullet at a tissue paper. He was expecting that bullet to pass right through. And if I were to draw some atoms here, right, if I were to draw atoms that make up this gold foil, I know I'm only showing one layer thick, but the idea is that, well, this is what happened. So he found that a lot of these particles did pass straight through. So that is what he was expecting. So there were a lot of particles, a lot of these alpha particles that passed straight through. But surprising to him, some of these particles actually seemed to deflect. So the screen, right, where the particles showed up on the screen showed him what was happening here. So some of these particles seem to deflect. So we would say most, right? Most pass through, and some deflected. And then the shocker of it all, right? There were a few that actually bounced straight back. And so you can imagine this detector, okay, coming all the way around so that it could pick up those particles that were reflecting. And so there were a few that reflected. So knowing that opposite charges attract, right, they also knew that like charges repel. So if you're sending positive particles at the atom and boom, it's going to bounce right back, he inferred that this positive charge that Thompson thought was spread throughout the atom is actually very concentrated. It's packed right into the small center of the atom. And why is it so small? Well, how could most of these positive particles pass through? If they were hitting positive charge, they would have been scattering and bending and maybe reflecting. So he inferred that most of the atom is actually empty space. So if we drew the circle, he would put the very positive center, right? And this would be a very small, right, dense, positive center of the atom. Okay, he made this center be very small compared to the rest of the atom. Most of the atom is empty space. This is Rutherford's inference. So why is he saying that? Well, because most of the particles are passing through undetected. So this observation here leads to this inference, and this observation here leads to this inference. Okay, so Rutherford contributed the idea really of a nucleus, that we have a very positively charged center of the atom. It's very small and densely positive. Okay, along came Bohr. So what did Bohr say? Oh, what did Rutherford say about the electrons? They were basically, somewhere out in this empty space. Okay, sometimes his model is called the planetary model. You'll see the electrons kind of positioned around that nucleus. People sometimes draw it like this, so the electrons are out here, moving around there. So this, is the planetary model. So this is Rutherford's idea. It's really all about the nucleus, okay? That's Rutherford's main contribution. Okay, and then we get to the Bohr model. So, wow, did Bohr ever propose something radical? He said, okay, we do have the nucleus in the middle, but electrons travel in fixed paths, in a predictable path, if I maybe change color here, in a predictable path around the nucleus. Okay, so Bohr called these paths here orbits, and he said that the electron could either be in the first orbit or it could be in the second orbit, right? This would be the second orbit here. So the first orbit is closest to the nucleus, the second orbit. The idea is that electrons had to be in one of these particular orbits or energy levels, right? There's a third and a fourth, but they couldn't hover in between. He also said that electrons, when they're energetically excited, like in the case of a firework, those electrons move up to higher energy levels, higher orbits, and then they fall back down, releasing light. So when you see the light given off, the colored light from a firecracker, that's the idea of these electron transitions that Bohr was discussing or proposing. And so this was pretty revolutionary and turned out to not be entirely accurate because the quantum model of the atom is the current model of the atom. And yet, we can cover a lot of basic introductory chemistry using Bohr's model. The experimentation that he used was called the emission line spectrum. Okay, and he focused particularly on hydrogen. Alrighty, so that's a very brief summary of the people involved in the history of the atom in our, introductory story here of the history of the atom. So we go really from Democritus's thought experiment, we move into the scientists, right, with their scientific experimentation, Dalton, Thompson, Rutherford, and Bohr.